Hello friends, so today we are going to solve the questions from the year 2001. There are total 4 questions. From the year 2002 there are 2 questions, and from the year 2003 there are also 2 questions. So total we are going to solve 8 questions. First question, it was asked in the year 2001, and it states that a uniform electric field pointing in positive x direction exists in a region. Let A be the origin, B be the point on the x-axis at x is equal to +1 centimeter, and C be the point on y-axis at y is equal to +1 centimeter. Then the potential at the points A, B and C satisfy. Okay, so we are given 3 points with their respective coordinates. So we can draw an approximate figure for that, and we are given 3 points, and it says that point A is at the origin, so its coordinate will be 0, 0. Point B is on x-axis, positive x-axis, so its coordinate will be 1, 0. And we have point C which is on y-axis, so this is point C, and coordinate will be 0, 1. And it says that the electric field is pointing in positive x direction, so the positive x-axis is the representation of the electric field, and we have to find out the potential at these 3 points, which of the condition it is being satisfying. And we know that the relationship between electric field and the potential, we know that the electric field is equal to minus dV upon dx, and we also know that the electric lines of forces flow from a higher potential to lower potential. Okay. And we can also say that electric lines of forces flow from higher potential to lower. Higher potential to lower potential. And if we see this graph, we can clearly understand that point A and point C both will be at the same potential, because if we draw the equipotential lines, okay, so we can say that the potential at A will be equal to potential at C. We can say our VA is equal to VC, okay. And this is same equipotential lines. And we can also say that our VA will be greater than our VB. Therefore, option number VA is greater than VB. Option number B is the correct one. Option B is correct. Next question. It was asked in the year 2001, and it states that consider the situation shown in the figure. The capacitor A has a charge Q on it, whereas B is uncharged. The charge appearing on the capacitor B a long time after the switch is closed is. So here we are given two capacitors A and B, and capacitor A is having a charge of plus and minus, and this B is our uncharged, and we have to find out the charge on B. So this we can say discuss using two approaches. First one is that the charge is only going to flow when the circuit is complete, which basically means that if this is switch S and we have a capacitor C, if the switch is open, there will be no current flowing in this circuit, and as soon as this switch is closed, both the plates are connected using this switch. Then only the current, or we can say for this the given figure, the charge transfer is going to take place. So in this particular case, we can clearly see that this circuit is not complete with the as per the connection between A and B. Only the two plates are connected and other two plates are not connected with each other. So because of this, there will be no charge transfer between the two. Okay. So we can say the charge appearing on capacitor B will be equal to 0. So we can just write the explanation. We are given that we have a capacitor A, and this capacitor A is charged, and it is having a charge of plus Q and minus Q respectively on the plates. And we have our capacitor B, and this capacitor B is our uncharged. Now if we close the switch S, the inner plates of both the capacitors are connected. Okay. So you can say that inner plates are connected via switch. Okay. But the outer plates are floating, which means not connected to each other or not connected to ground anyways. Okay. So circuit is basically not complete, so we are saying that they are floating. So for in this particular case, we can say they are not connected with each other, or we can say grounded. So therefore the charge will be equal to 0. And there is other concept that is based on the force. So we can say that this negative charge which is on plate A is tightly bound by the positive charge on the plate A. Okay, because of this there is no charge transfer, or we can say the charge does not flow. So we can this second approach also, and it states that positive plate attracts the negative plate. The negative plate. So no charge flow. So therefore option A is correct. Option A is correct. Next question. And it was asked in the year 2001, states that in the given circuit with steady state current, the potential difference across the capacitor must be, and we are given the circuit. We are given, you can see R, C and 2R, all these distances in parallel with the respective voltage of V, V as well as 2V. And here we have to find out the steady potential difference across the capacitor under steady state condition. And we know that under steady state condition the capacitor will be acting as an open circuit. So you can say that under steady state capacitor C acts as open circuit. Therefore we can say that the current flow through the capacitor C will be equal to 0. So we can just redraw the circuit. This is resistance R, and we have this capacitor will be now acting as open circuit, and we have so this is our V, voltage V, 2V and 2R. So there will be no current that will be flowing through the circuit, capacitor circuit rather. Okay. So from here the value of current will be equal to 0. So let us say the current I flows through here, and obviously same current will be flowing through here also. Okay. And we can use the KVL, so we can just draw its equivalent circuit, and that equivalent circuit will be something like this. See our R, V, 2V and 2R, current flowing through here is our I. So we can use the KVL. Or we can also use the Ohm's law. Ohm's law is our net voltage divided by net current. So we can say that the current I will be equal to both the voltage sources 2V as well as V are opposite to each other. So net voltage will be coming as 2V minus V, and the resistance are in series. This comes as 2R plus R. And we get from here that the current I will be equal to V upon 3R. So this is the current that will be flowing through the circuit, and we are supposed to find out the potential difference through the capacitor. Okay, and for that let us redraw the circuit, and see R, V, and this is a voltage source, and this is a capacitor here. Let us call this as point A and this point as B. Although the current through this is 0, but potential difference will be always present. And here we can just use our KVL. So we can write that current through the circuit we already know is our I. So I will be flowing in this direction, and value we already know is our V by 3R. So we can say that our, let us put the voltage here is VA and here is our VB. So we can say our VA minus, and we can just take the loop, VA minus V, and this will be a plus V, and this comes as, this will be plus and minus, so there will be rise in potential. So it comes as plus RI is equal to VB. V and V cancels out, so we get our VB minus VA is equal to R times I, and I we already know is our R into V upon 3R. R and R cancels out, so we get VB minus VA is equal to V by 3. So this is the potential difference across the capacitor. So we get option number C is the correct option. Option C is correct. Next question. It was asked in the 2001, and it states that a small ball of mass 2 into 10 to the power minus 3 kg having a charge of 1 microcoulomb is suspended by a string of length 0.8 meter. Another identical ball having the same charge is kept at the point of suspension. Determine the minimum horizontal velocity which should be imparted to the lowest ball so that it can make a complete revolution. So we are given, let's draw its basic figure. So we have a, let us suppose this is a center, and this is a string, and a horizontal velocity is imparted at the lowest point. Let us suppose that is our U, and we want that it should be making a complete revolution. So let us suppose it makes a revolution something like this. And the charge at the center, this charge over Q, and here also there is having a same charge. So here the charge is also given as Q, and this is thread, so the tension will be acting in upward direction, and charge is Q and mass is M. So we are going to have mg in the downward direction, and also there will be a force of repulsion between the charge at the center and charge at the end of string. Let us call this as force as F. And suppose this is the vertical topmost point, and here its velocity is suppose given as V, and this can say, let us call this tension as T1, and here there will be tension T2, and there will be mg in the downward direction, but the force of repulsion between the center charge and will be in the this way. Okay, and okay, so these are the basic basic things which we are going to require. And this center is O, lowest point let us suppose is A, highest point is let us suppose our B. Okay, and we need that just to complete one revolution. Under this condition, the tension at the topmost point, that is at B, this T2 should be equal to 0. That is the basic premise of this, you can say, discussion. And we can write the equation for point B. So you can say at point B, the net force, that is about T2, and this will be plus mg minus, and the force F that will be acting will be equal to 1 upon 4 pi epsilon naught, and this charges are same, so this comes as q square, and the distance between the two, let us suppose the length is given as L. So this is our length L, and this will be also length L. So this comes as our L square. So we get this as 1 upon 4 pi epsilon naught q square, and this comes as our L square, which will be equal to the required centripetal force, that is our mv square upon L. And we know that for ball to complete the circle, T2 should be equal to 0. Okay, it means at highest point this tension should be equal to 0. So therefore we substitute T2 is equal to 0. We can write the equation that our mg minus 1 upon 4 pi epsilon naught, and this is our q square upon L square is equal to mv square upon L. Now we can use also the conservation of energy for point A as well as for point B. You can say conservation of energy, so you can say energy at A, total energy at A should be equal to total energy at B. A is the lowest point, so here the potential energy will be equal to 0. Only energy that will be present will be the kinetic energy with the velocity of u. Therefore we can write total energy, or we can just divide it. We can write our potential energy at A plus kinetic energy at A will be equal to potential energy at B plus kinetic energy at B. And potential energy at A is equal to 0. So kinetic energy is our half m u square will be equal to potential energy at B will be equal to our mg, and total length is our 2L with respect to point A, and kinetic energy will be equal to half m v square. And this m and m cancels throughout, so we can write that our equation can say our we need to so we can say our V square will be equal to U square, and this comes as minus 4 GL. And from, let us call this equation number 1 and this as equation 2. So from equation 1 we can find out our V, because we are only interested in one, that is our U, that the energy velocity at the lowest point. So we are going to replace this V, and in order to find out V we are going to make use of equation 1. So you can say from equation 1 we can write that our V square will be equal to, we divide it by L and M, so we get this as GL minus 1 upon 4 pi epsilon naught, and this comes as Q square and M multiplied by L. So we substitute value of V, and we get this as GL minus 4 pi epsilon naught Q square ML is equal to U square minus 4GL, and 4GL and this is GL, so this will be coming as 5GL. So therefore we can write that our U square is equal to 5GL minus 1 upon 4 pi epsilon naught Q square mass into length. Or from here we can say our U is equal to 5GL minus 1 upon 4 pi epsilon naught Q square upon multiplied by ML and its square root, and we are given all the values, so we can substitute the values. So we can say our U will be coming approximately as 5.86 meter per second. So this is the value of the U, that's the lowest point, so as to complete one revolution. Next question. It was asked in the year 2002, and it states that two identical capacitors having same capacitance C, one of them is charged to potential V1 and other to V2. Likely charged plates are then connected. Then decrease in the combined system is. So here we are having two capacitors and they are having same capacitance. So we can just draw an approximate figure. So this is our capacitor 1 C1 and it is connected to capacitor C2, and it says that likely charged plates are connected with each other like this. And its potential is V1, potential is given as V2, and we have to find out the decrease in the energy of the combined system. So we know that the energy stored in the capacitor is half CV square, and in this case, as they are likely charged plates are connected with each other, so the capacitance will be in parallel, so the net capacitance will be their direct sum. So here we are given there are two capacitors and they having same capacitance, that is C1 is equal to C2 is equal to C, and we are given that C1 is having a potential of V1 and C2 is having a potential of V2. And so in this case, the final potential across the parallel combination will be same for both the capacitor. We can say find out that later on also. Okay, let us start with our energy that is required. So we can just find out the energy before they are connected with parallel with each other. So we can call this initial energy of each capacitor. So we can see initial energy of each capacitor. So let us, for C1, let us call this energy as U1, and that will be equal to over half C1 V1 square, and C1 is our C, so this comes as half C1 square. Similarly, for our C2, let us call that as U2, which will be equal to half C2 V2 square, coming as half C V2 square. So the total energy of the system will be the summation of both. Therefore, we can say total initial energy let us call that a UI will be equal to U1 plus U2. Therefore, we can write that our UI will be equal to, we can take half C as common, so this will be for V1 square plus V2 square. So this is our initial energy, and we can also find out what will be the respective charges on that. Okay. So let me write it here only. So charge on C1, if that is given as Q1, so this will be equal to C times V1, and charge on C2 that is given as Q2 will be equal to C times V2. So the total charge, that is our Q initial, will be equal to Q1 plus Q2. C we can take common is our V1 plus V2. Okay, we have to remember that before and after the charges will be conserved. Okay. And so now when they are connected with each other, so you can say when capacitors C1 and C2 are connected and they will be in parallel, and parallel we can find out their equivalent capacitance. So we can say our C equivalent will be equal to C1 plus C2, which becomes as C plus C, giving us C equivalent will be equal to 2 times C. So this is the equivalent capacitance of their combination, and we can find out their final potential energy. So you can say the final potential, not energy, then we are going to find out potential energy. So final potential, let us suppose that is given as Vf, and this is final potential energy, final potential, that is Vf, will be equal to our charge final divided by the C equivalent. And according to the conservation of charges, our Qf will be equal to Q initial, that comes as, we have already found it. So this comes as Q initial divided by C equivalent, and we just substitute the value, we get our final potential, that is Vf, and Q initial is our C V1 plus V2, and C equivalent we found out is our 2C, and here the C and C cancels out, therefore we get our final potential will be equal to V1 plus V2 divided by 2. Now we can find out the final energy of the system. Final energy of the system, let us call that as UF, will be equal to our half C equivalent and Vf square. So we get our UF is equal to C equivalent is our 2C, and Vf square is our V1 plus V2 divided by 2 and its whole square. And we can just sort it out, and this will be coming as C by 4, and this can be written as V1 square plus V2 square plus twice V1 V2, and we have to find out the decrease in the energy. So we can say decrease in energy, let us call that delta U will be equal to our U initial minus U final. We already know both the equations, so we get U initial was our half C V1 square plus V2 square, and this is minus C by 4, and we get V1 square plus twice V1 V2 plus V2 square, and we can take C by 4 as common. So here let us divide and multiply by 2, and so this comes as C by 4 will be common, so this comes as C by 4, and we are left with 2 V1 square plus 2 V2 square minus V1 square minus twice V1 V2 minus V2 square. And now it is quite easy, we can write this will be equal to C by 4 is our common, this is our V1 square and V1 square, so we have left with only V1 square, and this is V2 and V2, so this comes as plus V2 square minus twice V1 V2, and this will be coming as V1 minus V2 whole square. Therefore we can say our decrease in energy, that is delta U, is equal to C by 4, and this comes as V1 minus V2 and whole square. Therefore we get this as option number C is the correct one. Option C is correct. Next question. It states that it was asked in the year 2002, and it states that two equal point charges are fixed at x is equal to minus a and x equal to plus a on the x-axis. Another point charge q is placed at the origin. The change in the electrical potential energy of q when it is displaced by a small distance x along the x-axis is approximately proportional to. So in this case we are given that we have two charges. So we can just draw the approximate figure for that, and the coordinate of these two charges, equal charges are there. So let us suppose this is our Q placed at minus A, and this is our other charge Q placed at plus A, and we have capital Q which is placed at origin. So suppose this is our origin, and here we have placed capital Q. So the distance will be A, and this distance will be also over A. And now it states that or we can also write it here, the x is equal to minus of A, this will be x equal to 0, and here x will be equal to our plus of A. Now it states that the point Q is displaced by a distance of x. So we can just redraw the figure, and the position of charge is this Q is still at x equal to minus A, and the other charge is still at x is equal to A. But the new position of the charge Q, capital Q rather, is displaced at the position x is equal to x. And therefore, this was our original position. It is displaced by a distance of x. So we can just find out the distance. This distance will be coming as A plus x, and the other distance will be coming as A minus x. And we have to find out the change in the potential energy. Okay, so we have this as an initial, and this is our final. So for initial energy with respect to point Q or charge Q, because it is equidistant from both, so it will be twice of the individual energies. So you can say initial energy, that is our, let us suppose UI will be equal to, normal energy formula is 4 pi epsilon naught, the product of the charges and the distance between them, that is A, and obviously we have to multiply it by 2 because they have the same charges and the distance is also same. Now we are going to find out the final energy. Let us call that as UF, and that will be equal to 1 upon 4 pi epsilon naught. Now the distance between the charges is different, so obviously it will be coming as on the one side x plus A plus x, and plus this will be coming as A minus x. And we can just solve it. We get this as our U final will be equal to 1 upon 4 pi epsilon naught, and this coming as Q, and this will be our LCM is A minus x. Okay, let me write it in this way. This comes as Q, and we have here 4 pi epsilon naught, and denominator will be coming as A square minus x square, and numerator will be coming as A minus x plus A plus x, which will be our 2A. And we are only interested in this part because we need some kind of approximation, so we can solve it. So this will be coming as Q 4 pi epsilon naught, and here we have 2A, and we can take as A square as common, so this comes as 1 minus x square by A square. This can be further written, and we get this as Q multiplied by Q 4 pi epsilon naught, and this comes as 2a by a square, and this is 1 minus x square a square raised to power minus 1. So we can just approximate it, especially this term, and we can write this as the square goes by this a, so this comes as 2q upon 4 pi epsilon naught, and multiply by a, and it comes as 1 plus x square by a square. Now we can easily find out the change in energy, that is our delta U will be equal to our UF minus UI, which will be giving us 2QQ, and this is our 4 pi epsilon naught multiplied by A, and that is our let's open it, and this comes as plus, this comes as 2QQ upon 4 pi epsilon naught A multiplied by x square divided by a square, and minus, we are left with 2 into QQ upon 4 pi epsilon naught and multiply by A, and these two terms cancels out, therefore we get this is equal to 1 upon 4 pi epsilon naught, and here we are left with only 2QQ upon a cube and multiply by x square, and we need to find out that approximation. So from here we can say this our delta U is proportional to our x square. So therefore option B is the correct one. Option B is correct. Next question. It was asked in the year 2003, and it states that a positive point charge Q is fixed at origin. A dipole with a dipole moment P is placed along x-axis far away from the origin with P pointing along positive x-axis. Find part A, the kinetic energy of the dipole when it reaches a distance d from the origin, and part B, the force experienced by the charge Q at this moment. So we are given that we are having a dipole and there is a charge fixed at the origin. Okay. So we are given that point charge is fixed at origin and the dipole is initially very far away and it is brought So we know that obviously there will be change in the potential energy of the dipole, and we can say that the change in potential of a dipole in electric field, that is given as minus P dot E, where E is the electric field. So let's calculate the change in potential energy of the dipole. So you can say the change in potential energy of dipole, and we know that the potential energy of a dipole in an electric field that is suppose given as u will be equal to minus p, sorry, it is given as small p dot E, and E is the electric field, and this electric field is because of the point charge Q. So we can say E is the electric field of a point charge Q. So we can write our electric field E will be equal to 1 upon 4 pi epsilon naught Q divided by R square. Okay, electric field of point charge Q at distance R. At distance R. And now this is our basic formula, and we can divide this on the basis of our initial and final position of the dipole. And final position it stays is at a distance of d. Therefore we can say that our u final will be equal to minus p, and this comes as 1 upon 4 pi epsilon naught q upon d square, because now dipole is at a distance of d, so we replace our r by d. Okay. And the u initial, we can assume that the dipole is very far away, so its initial energy is equal to 0. So we can say u initial is equal to 0. And here we assume that potential is 0 at infinity. Potential is 0 at infinity. Therefore, the change in potential energy, our delta U will be equal to our U final minus U initial, which comes as minus PQ, and this is 4 pi epsilon naught d square. And we also need to find out the kinetic energy, and for that we can use the conservation of energy. So we can say the kinetic energy of dipole we can say by conservation of energy, the change in kinetic energy, is equal to negative of change of potential energy. Negative of change in potential energy. Therefore, we can say that our kinetic energy final will be equal to minus of delta U. So we get this as delta U we just found out. So we get this as P times Q, and we get this as 4 pi epsilon naught d square. And I think we need to find out the force, kinetic and the force. We found out the kinetic energy, and now we are going to find out the force. And we can find out now the kinetic energy at origin due to the dipole. Sorry, not kinetic energy, but electric field. Electric field at the origin due to dipole. And that electric field, let us suppose, is given as ED. D stands for dipole, and that will be equal to 1 upon 4 pi epsilon naught, and this is 2 times P divided by R cube, and here R will be equal to our D. Therefore, we can say that our electric field due to dipole will be equal to 1 upon 4 pi epsilon naught 2p divided by d cube. Now we can find out the force experienced by the charge at the origin. Force experienced by the charge, and that charge is our Q, at the origin. Let us suppose that force is F, so that will be equal to Q and multiply by electric field due to the dipole. Now we can simply substitute the values. We get that the force will be equal to, this comes as Q times 1 upon 4 pi epsilon naught twice P divided by d cube, and we can just rearrange it, and we can write this as 2 key P divided by 4 pi epsilon naught, and this is our d cube. So this was the force as well as the kinetic energy. And if we want to with respect to direction also, so we can put the direction also. So direction here will be our I unit vector, and this will be also our I unit vector if required. Next question. It was asked in the year 2003, and it states that the 8-point charges are placed in the corners of a cube of H A as shown in the figure. Find the work done in disassembling this system of charges. So we are given a cube and whose side is given as A. And from, you can say, first of all, in this case, we have to find out the number of charge pairs, and the number of charge pairs, we can use the formula, and we can say number of charge pairs will be equal to our n minus 1 divided by 2, and total are 8-point charges, so value of n is 8, so this comes as 8 minus 1 divided by 2, and this comes as 7, 4, and this is our 28. So total number of charge pairs are 28. And here we have to find out, because we have to find out the disassembling. So in this case, we have to segregate the number of charge pairs in terms of opposite charge as well as the similar charge. Okay, and so we have to divide this into under two parts. one is of opposite charge and other will be of similar charge. And they need to be further segregated based on where this opposite charge as well as similar charge are placed, means with respect to their distances. And if we see this particular figure, we can understand that the similar charges are always on the same phase. So it means the distance between these two charges will be equal to square root of square root of 2 times A. Okay. And here also we can see that these are the similar charges, and here also the similar charges, and likewise on the opposite side also there are similar charges. So all these similar charges are at the same distance. Okay. So these similar charges, they are at a distance of, you can say, root 2 times A. So this is the distance. Similar charges at distance of square root 2 times A. Whereas, and these similar charges will be our 12 pairs. So this will be our 12 pairs of similar charges, and the opposite charges are at different, you can say, distances. Okay. So we can say these opposite charges are at the different distances. From here we can say they are at a distance of A, and along with this they are also at a distance of this distance. Okay, and that distance will be square root of 3 times A. So opposite charges are at two different distances, and one distance is of A, and the number of pairs for this particular distance are 4 pairs, and other are the distance of square root of 3 times A, and the number of pairs total are 28, so this will be 12 pairs. Here we are only interested in pairs because we have to find out the work done, or basically we can say energy, and energy is always with respect to two charges, whether they are same or they are different. Okay. So let us sort it out for similar charge. In the first case, okay, let's do for the opposite first. Okay, so this is our first case, and this is our first, second, third case. Okay. So for the first case we are having 4 pairs, and the distance between them is A. Let us call that energy as U1. So we can say our U1 will be equal to 4 times, and the charges are opposite, so this comes as Q multiplied by minus Q divided by, and one second, I think there is some, let me check. Opposite charges, root distance A. Okay, so this comes as 4 pairs, which are having a distance of, let me check whether they are 4 or not. This is 1 pair, 2 pair, 3 pair and 4 pair. 1, 2, 3, 4, 5, 6. Okay, it has to be 12. That is it. This is 12. This is 12 and this is 4. So we get this as 12 and at a distance of 4 pi naught and multiply by A. Okay. And this is 12 pairs. Next is second, and second we are having 4 pairs and at a distance of root 3 by A, through 3 multiplied by A, and let us call that as our U2. So U2 will be equal to 4 and this comes as our Q multiplied by minus Q 4 pi epsilon naught, and this is root 3 times A. And finally our third. And our third part is our similar charges with 12 pair. 12 pairs and the distance is our root 2 A, and we can write it as our U3 will be to 12 and this comes as 1 upon 4 pi epsilon naught. The charges are same and multiply by root 2 times A. We can find out the total energy. Total energy U will be equal to U1 plus U2 plus U3, and we can simply substitute them. So we get this as 1 upon 4 pi epsilon naught will be common, and this Q square upon A will be also common. Inside we get minus of 12 plus 12 root 2 and minus 4 root 3. And this will be approximately equal to minus 5.83 and 1 upon 4 pi epsilon naught Q square upon A. So work done will be negative of this energy. So we can say work done in disassembling will be equal to this minus of U, and which gives us plus 5.83 times 1 upon 4 pi epsilon naught Q square upon A. So this is our next question. Okay, so this complete all the questions. So the total question were our 8 questions. From 2001 we were having 4 questions, 2002 2 questions, and 2003 also 2 questions. So total 8 questions. So this completes all the 8 questions. Thank you.